Okay, in this lecture we will study conditional expectation. Let's start with section 1, conditional expectation given a non-trivial event. First, consider a probability space which we denote omega script f p, and let's take an event b within our sigma algebra script f such that its probability p of b is greater than 0. Then, as you recall, the conditional probability of any event a in script f given the event b is defined as the probability of a given b equals the probability of a intersect b, all divided by the probability of b. Now let's bring in a random variable x, mapping from omega to the real numbers, defined on this same probability space with its distribution function f sub x mapping reals to the interval 0, 1. And again, we'll consider a non-trivial event b in script f, meaning the probability of b is positive. We can now define the conditional distribution. The conditional distribution of x given the event b is denoted by f sub x vertical bar b mapping reals to 0, 1. F sub x given b evaluated at x is defined as the probability of the event a sub x of x conditioned on b for all real x. Here a sub x of x is just the event that our random variable x is less than or equal to x. So f sub x given b of x is the probability that x is less than or equal to x given b, which by definition is the probability of the intersection of the events x less than or equal to x and b divided by the probability of b. This holds for all real x. Just a reminder, this conditional distribution f sub x given b is indeed a valid distribution function. This follows because first, f sub x given b is always non-negative. Second, its right continuous, and third, its limit as x goes down to minus infinity is 0, and its limit as x goes up to infinity is 1. Another reminder, specifically for a discrete random variable x mapping omega to a countable set script x, the conditional probability mass function of x given a non-trivial event b is given by p sub x given b of x, which equals the probability that x equals x, and b occurs divided by the probability of b. This holds for all x in the support script x. And for a continuous random variable x mapping omega to the reals, the conditional density of x given a non-trivial event b is given by f sub x given b of x, which is the derivative of the conditional distribution function f sub x given b of x with respect to x for all real x. Let's look at an example of conditional distribution. Consider the probability space corresponding to rolling a fair die once. In this case, the outcome space omega is the set 1, 2, 3, 4, 5, 6. The event space script f is the power set of omega, and the probability measure p assigns 1/6 to each outcome omega in omega. Now let's define a random variable x mapping omega to the reals such that x of omega simply equals the outcome omega, Let's also define an event B as the set of outcomes where x is less than or equal to 3, which corresponds to the set 1, 2, 3. We can see that the probability of B is 3/6 or 1/2. The conditional probability mass function of x given B, P sub x given B of x, is then 1/3 if x is 1, 1/3 if x is 2, and 1/3 if x is 3, and 0 otherwise. With the conditional distribution defined, we can define the conditional expectation. The conditional expectation of x given event B is given by the expectation of x given B, defined as the integral over all real x of x times df sub x given B of x. As a reminder, for the discrete case, if x is a discrete random variable mapping omega to script x, the conditional expectation of x given a non-trivial event B is the sum over all x in script x of x times the conditional probability P sub x given B of x. Let's continue our fair die example. For the random variable x and event B, we defined where x is the outcome and B is the event that x is less than or equal to 3. The conditional expectation of x given B is calculated as 1 times 1/3 plus 2 times 1/3 plus 3 times 1/3, which sums to 6/3 or 2. Now let's pause and think. If we have two random variables, x and y, on the same space, then for a value y such that the probability y is less than or equal to y is positive, we can define the conditional probability that x is less than or equal to x, given that y is less than or equal to y. This equals the joint distribution function f sub x y of x, y divided by the marginal distribution f sub y of y. The key here is that the event y less than or equal to y is a non-trivial event. But how would we define conditional expectation based on an event like y equals y? If y is a continuous random variable, this event typically has a probability measure of 0, which poses a challenge to our previous definition. This leads us to the concept of conditional expectation given an event space or a sigma algebra. Consider two random variables, x and y, mapping omega to the reals, defined on the same probability space, omega, script f, p. Assume that x is integrable, meaning the expectation of absolute x is finite. Let script G be a smaller event space, a subsigma algebra of script F for each non-trivial event, G in script G, meaning probability of G is positive. We know how to define the conditional distribution F sub x given G and the conditional expectation of x given G. These are undefined for trivial events, n in script G, those with probability 0. So we define the conditional expectation of random variable x given the event space script G. This is itself a random variable which we denote expectation of x given script G mapping omega to the reals defined on the same probability space. It must satisfy three properties. First, let's call this new random variable Z, defined as expectation of x given script G. Z must be script G measurable. This means that the pre-image under Z of any interval minus infinity to y must belong to the sigma algebra script G for all real y. Second, the averaging property must hold for all events G in the sigma algebra script G. The expectation of X times the indicator of G must equal the expectation of Z times the indicator of G. Third, Z must also be integrable, meaning the expectation of the absolute value of Z is finite. An important lemma states that this conditional expectation of X given script G is an almost surely unique random variable. Let's sketch the proof. Suppose we had two such random variables, Z1 equals expectation of X given script G, and Z2 equals expectation of X given script G. By definition, both Z1 and Z2 are script G measurable, which implies their difference, Z1 minus Z2, is also script G measurable. Therefore, the event Gn defined as the set where Z1 minus Z2 is greater than 1 over n must belong to script G for any positive integer n. By the defining property of conditional expectation, property 2, the expectation of the difference Z1 minus Z 2 times the indicator of Gn must be 0. Using properties of expectation and limits, specifically the continuity of probability, we can show that the probability of the limit of Gn as n goes to infinity is 0. This limit represents the event where Z1 is strictly greater than Z2. Similarly, defining Fn as the set where Z2 minus Z1 is greater than 1 over n, we can show the probability of the limit of Fn is also 0. Together, this implies that Z1 must equal Z2 almost surely. Let's consider two extreme examples to understand conditional expectation as a form of averaging. Consider a random variable x on omega, script f, p, with finite expectation of absolute x. Let's take the coarsest possible event space, script g equals just the empty set and the whole space omega, which is a subset of script f. And let's also consider the finest event space, which is script f itself. We observe that the conditional expectation of x given the trivial sigma algebra script g is simply the constant value expectation of x. Almost surely, this holds uniquely because first, the constant expectation of x is certainly measurable with respect to the trivial sigma algebra script G. Second, the averaging property holds. Expectation of expectation x times indicator empty set is 0, which equals expectation of x times indicator empty set. And expectation of expectation x times indicator omega equals expectation x, which equals expectation of x times indicator omega. Third, the integrability holds. Expectation of absolute value of expectation x is just absolute value of expectation x, which by Jensen's inequality is less than or equal to expectation of absolute x, which we assumed is finite. We also observe that the conditional expectation of x given the original sigma algebra script f is just x itself. Almost surely this holds uniquely because first, x is by definition script f measurable. Second, the averaging property is trivially satisfied. Expectation of x indicator g equals expectation of x indicator g for all g in script f. And third, we assumed x is integrable. Expectation of absolute x is finite. Another key property, often called the tower property or law of total expectation. The mean of the conditional expectation of x given script G is just the mean of x. The proof is simple. By definition, the whole space omega is in the sigma algebra script G. Using the averaging property part 2 of the definition with G equals omega, we get the expectation of the conditional expectation of x given script G equals the expectation of x given script G times indicator omega, which must equal the expectation of x times indicator omega, which is simply the expectation of x. Now we can define the conditional expectation given another random variable. The conditional expectation of x given y is defined as the conditional expectation of x given the sigma algebra generated by y, sigma of y. That is, expectation of x given y is defined as expectation of x given sigma of y. Let's look at an example, conditioning on simple random variables. Suppose y is a simple random variable mapping omega to a finite or countable set script y contained in the reals defined on our probability space. We can define the fundamental events E sub y as the pre-image of y under y for each y in script y. These events E sub y belong to the sigma algebra script F. Then the sequence of these events, E consisting of E sub y for all y in script y, forms a partition of the sample space omega. The event space generated by y sigma of y consists of all possible unions of these fundamental events E sub y, where we take unions over any subset I of the possible values script y. Now consider another random variable x mapping omega to the reals on the same space. The random variable z defined as the conditional expectation of x given y must be sigma of y measurable. Since z is sigma of y measurable and sigma of y is generated by the partition E sub y, z must be constant on each event E sub y. Therefore, we can write the expectation of x given y as a sum over y in script y of some constant alpha sub y times the indicator function of the event E sub y for some set of coefficients alpha in R to the power script y. We can verify that z defined this way is indeed sigma of y measurable because the sigma algebra generated by z is clearly a subset of sigma of y. We also need to ensure z is integrable, which follows from the integrability of x. We can check that the expectation of absolute z is finite. Continuing with conditioning on simple random variables, the averaging property tells us that the expectation of z times indicator E sub E must equal the expectation of x times indicator E sub y for any y in script y. Since z equals alpha sub y on the event E sub y, the left side is expectation of alpha sub y indicator E sub y, which is alpha sub y times the probability of E sub y or P sub y of y. Thus, alpha sub y times P sub y of y equals expectation of x indicator E sub y. Solving for alpha sub y assuming P sub y of y is positive, we find that alpha sub y equals the expectation of x indicator E sub y divided by P sub y of y. Notice that this value alpha sub y is precisely the conditional expectation of x given the event E sub y that we defined earlier using conditional distributions. Recall, expectation of x given E sub y is the integral of x d. F sub x given E sub y of x. This integral equals 1 over P sub y of y times the integral of x d P of A sub x of x intersect E sub y, which can be shown to equal 1 over P sub y of y times the expectation of x indicator E sub y. So indeed, alpha sub y is the expectation of x given the event E sub y. So let's recap the main takeaways from this definition. First, for a random variable y, the event space it generates is sigma of y. The conditional expectation of x given y is the same as expectation of x given sigma of y, and crucially it is measurable with respect to sigma of y. This means that the conditional expectation of x given y can always be expressed as some Borel measurable function of y. In particular, when y is discrete or simple, this implies expectation of x given y is itself a simple random variable. It takes the value expectation of x given E sub y whenever the outcome omega falls into the event E sub yi when y equals y, and the probability of this occurring is P sub y of y. When y is continuous, the conditional expectation of x given y will generally be a continuous random variable related to the density f sub y. Second takeaway, expectation is averaging. Conditional expectation is averaging over specific event spaces. We saw that the coarsest averaging expectation of x given the trivial sigma algebra empty set omega just gives the overall average expectation of x. The finest averaging expectation of x given sigma of x, the information in x itself just gives back x. Furthermore, expectation of x given sigma of y represents the averaging of x over the events generated by y. If we take any event A that belongs to sigma of y, meaning A's occurrence is determined by the value of y, then the conditional expectation of x given y is fine enough to determine the average of x when this event A occurs. Mathematically, this is the averaging property. The expectation of x times the indicator of A equals the expectation of the conditional expectation of x given y times the indicator of A. Third takeaway, if x is in L1 integrable, then its conditional expectation of x given y is also in L1 integrable. Now let's move to section 2, conditional distribution given an event space. We can define the conditional probability of an event A in script F given an event space or subsigma algebra script G. We denote this P of A given script G and define it as the conditional expectation of the indicator function of A given script G. That is, P of A given script G is defined as expectation of indicator A given script G. From our definition of conditional expectation, it follows that this conditional probability P of A given script G is a script G measurable random variable mapping omega to the interval 0, 1. It satisfies the averaging property. The expectation of indicator G times P of A given script G equals the probability of A intersect G for all G in script G. And it's uniquely defined up to sets of probability 0. As an example, for the trivial sigma algebra script G containing only the empty set and omega, the conditional probability P of A given script G is just the constant function equal to the overall probability P of A. Another example, if the event A itself belongs to the sigma algebra script G, then the conditional probability P of A given script G is simply the indicator function of A. Now we define the conditional distribution given an event space. The conditional distribution of a random variable X given a sub-event space script G, denoted F sub X given script G of X, is defined as the conditional probability of the event A sub X of X, which is X less than or equal to X given script G for all real X. Recall that for each fixed X F sub X given script G of X is a script G measurable random variable mapping omega into 0, 1. Furthermore, if we view F sub X given script G as function of X for a fixed outcome omega, we observe that it's monotone, non-decreasing in X, it's right continuous at all X, and its limits are 0 as X goes to minus infinity and 1 as X goes to plus infinity. It follows that F sub X given script G can be viewed as mapping omega to the space of distribution functions. It's a random distribution function. A key theorem connects this conditional distribution to conditional expectation. Let G be a Borel measurable function from reals to reals, and let script G be a sub-event space. Assume expectation of absolute G of X is finite, then the conditional expectation of G of X given script G equals the integral over all real X of G of X integrated with respect to the conditional distribution df sub X given script G of X. Let's sketch the proof for the case where X is a simple random variable mapping omega to script X. Since G is Borel measurable, G of X is also a random variable. We will show that the expectation of G of X given script G equals the sum over X in script X of G of X times the conditional probability P sub X given script G of X by verifying the three defining properties of conditional expectation. For part 1, measurability, from the definition of conditional probability P sub X given script G of X is a script G measurable random variable for each X in script X. Therefore, any finite linear combination like the sum over X in script X of G of X times P sub X given script G of X is also script G measurable. For part 2, the averaging property, let G be any event in script G. Then, using the linearity of expectation and the defining property of conditional probability, the expectation of the sum over X of G of XP sub X given script G of X times the indicator of G equals the sum over X of G of X times the expectation of P sub X given script G of X times indicator G. By the property of conditional probability, this equals the sum over X of G of X times the expectation of indicator E sub X intersect G, where E sub X is the event X equals X. This sum is precisely the expectation of G of X times indicator G. Continuing the proof for part 3, integrability, using the triangle inequality linearity of expectation and the definition or property of conditional probability, the expectation of the absolute value of the sum over x of g of x p sub x given script g of x is less than or equal to the sum over x of absolute g of x times the expectation of p sub x given script g of x. Since expectation of p sub x given script g of x is just p sub x of x, this becomes the sum over x of absolute g of x times p sub x of x, which is exactly the expectation of the absolute value of g of x. We assume this is finite. As a reminder, we can also define the conditional characteristic function. Phi sub x given script g of u equals the expectation of e to the ju x given script g, which equals the integral over x in r of e to the jux df sub x given script g of x. Now let's define the conditional distribution given a random variable. The conditional distribution of random variable x given random variable y, denoted f sub x given y of x, is defined as the conditional probability of the event a sub x of xx less than or equal to x given the sigma algebra generated by y, sigma of y. This holds for all real x. Let's revisit the example of conditioning on simple random variables. Consider a random variable x mapping omega to r and a simple random variable y mapping omega to script y, both on the same probability space. Since either the conditional distribution f sub x given y of x, which is the expectation of indicator a sub x of x given y, must be sigma of y measurable, it must be constant on the atoms E sub y, where E sub y is the event y equals y. Therefore, f sub x given y of x can be written as a sum over y in script y of some coefficient beta sub x comma I times the indicator of E sub y for some coefficients beta sub x that depend on y. Furthermore, the averaging property tells us that the expectation of f sub x given y of x times indicator E sub y equals the expectation of indicator a sub x of x times indicator E sub y for any y in script y. The left side simplifies to beta sub x comma E times p sub y of y. The right side is the probability of a sub x of x intersect E sub y. Thus, beta sub x comma E equals the probability of a sub x of x intersect E sub y divided by p sub y of y. We recognize this as precisely the conditional distribution f sub x given the event E sub y evaluated at x. It follows that f sub x given y is a simple random variable measurable with respect to sigma of y. It takes the value f sub x given E sub y of x on the event E sub y. Let's look at another example for conditional expectation. Consider a fair die roll and let x be the random variable representing the outcome. Omega is 1 to 6, script f is the power set, and x of omega is omega. The probability p sub x of x is 1/6 for x from 1 to 6. Now define another random variable y, which is the indicator that x is less than or equal to 3. So y is 1 if x is 1, 2, or 3, and y is 0 if x is 4, 5, or 6. Then the conditional expectation of x given y is a random variable. It's given by the expectation of x given y equals 1 times the indicator that y equals 1 plus the expectation of x given y equals 0 times the indicator that y equals 0. We calculated earlier that expectation of x given y equals 1, which is event b from before, is 2. If y equals 0, then x is 4, 5 or 6. So the expectation of x given y equals 0 is 4 plus 5 plus 6 by 3 equals 5. Thus, expectation of x given y is 2 times the indicator of y equals 1 plus 5 times the indicator of y equals 0. Since the probability that y equals 1 is 0.5 and the probability that y equals 0 is 0.5, we can check the law of total expectation. The expectation of expectation x given y is 2 times 0.5 plus 5 times 5, which is 1 plus 2.5 equals 3.5. And the expectation of x itself is also 1 plus 2 plus 3 plus 4 plus 5 plus 6 by 6 equals 21 by 6 equals 3.5. It matches. Here's an example involving conditional distribution. Consider a zero mean Gaussian random variable n with variance sigma squared. Let y be another independent random variable taking values -1 or 1 with probability mass function 1 minus p and p for some p between 0 and 1. Let x be defined as y plus n. Then the conditional distribution of x given the simple random variable y is f sub x given y equals f sub x given y equals -1 times indicator y equals -1 plus f sub x given y equals 1 times indicator y equals 1. Here f sub x given y equals mu represents the distribution function of a Gaussian random variable with mean mu and variance sigma squared, which involves the integral of the Gaussian density, something like integral from -infinity to x of e to the minus t minus mu squared over 2 sigma squared dt times the normalization constant. Now let's consider the case where x and y are both continuous random variables possessing a joint density f sub xy of xy for all xy in R squared for each y in the support of y such that the marginal density f sub y of y is positive. We can define a function f sub x given y mapping R squared to non-negative reals such that f sub x given y of xy is defined as the joint density f sub xy of xy divided by the marginal density f sub y of y. This holds for all real x. As an exercise for continuous random variables, x and y, show that the function which for a fixed y maps x according to f sub x given y equals y as defined above is indeed a valid probability density function for the continuous random variable x. Let's revisit conditioning on simple random variables to tie things together. Consider two random variables x and y on the same probability space. If y maps omega to a simple set script y, then the events e sub y, defined as y equals y, partition the sample space. Further, the simple random variable y has a PMF p sub y given by the probabilities p of e sub y for each y in script y. If y is in script y such that p sub y of y is positive, then we can define the function f sub x given e sub y mapping R to 0, 1 such that f sub x given e sub y of x is the probability that x is less than or equal to x given the event e sub y. This equals the probability that x is less than or equal to x and y equals y divided by p sub y of y from the definition of conditional distribution given an event. This holds for all real x. Here's another exercise. For a simple random variable y mapping omega to script y, show that the function f sub x given e sub y, condition on the event e sub y equals y, is indeed a valid distribution function. Let's formally define this again. Consider random variables x and y on the same probability space. If y is simple, mapping omega to script y, then for all y in script y with positive probability p sub y of y, we define the event e sub y as y equals y, and the conditional distribution of x given event e sub y is the function f sub x given e sub y mapping R to 0, 1 as defined in that previous equation. Now we define the conditional distribution of x given the random variable y. If y is simple with atoms e sub y for y in script PR, then the conditional distribution of x given y, denoted f sub x given y, which maps omega into the space of distribution functions, is defined as f sub x given y of omega equals the sum over y in script y of f sub x given e sub y times the indicator of e sub e evaluated at omega. As a reminder, we observe that f sub x given the event y equals y is just f sub x given e sub y. Hence, the conditional distribution f sub x given y is a measurable function of the simple random variable y, which can be written as sum of y indicator e sub y, and therefore f sub x given y is itself a random object, specifically a random distribution function. Now let's talk about conditional densities again. When x and y are both continuous with a joint density f sub xy of xy for each y such that the marginal density f sub y of y is positive, we can define a function f sub x given y equals y mapping R to non-negative reals such that f sub x given y equals y evaluated at x is defined as the joint density f sub xy of xy divided by the marginal density f sub y of y. This holds for all real x. And the exercise again show that this function f sub x given y equals y is a valid density function in x for each fixed y. Now we can put conditional expectation in terms of these conditional distributions. Since we've defined conditional distributions and densities, we can define conditional expectation given an event as an integration with respect to the conditional distribution given that event. In the following, we'll assume x and y are on the same probability space and that x is integrable, meaning expectation of absolute x is finite. So expectation x exists and is finite. First, for simple random variables, when y is simple mapping omega to script y, we can define the conditional expectation of x given the event e sub y, where e sub y is y equals y and p sub y of y is positive, as expectation of x given E sub y is defined as the integral over x in R of xd, f sub x given E sub y of x. This can also be shown to be equal to the expectation of x times indicator E sub y divided by P sub y of y. Now the conditional expectation given the random variable y itself. When y is a simple random variable, we define the conditional expectation of x given y as a measurable function of y. Denoted expectation x given y mapping omega to r such that its value at omega is given by the integral over x in r of xd f sub x given the event y equals y of omega of x. Hence, we can write expectation of x given y explicitly as the sum over y in script y of the conditional expectation given the event E sub y times the indicator function of E sub y. This equals the sum over y in script y of fraction expectation x indicator E sub y over P sub y of y times the indicator of E sub y. As a reminder, the random variable expectation of x given y takes the value expectation of x given E sub y with probability P sub y of y for all y in script y. And a key lemma, the law of total expectation for simple y. For a simple random variable y, the mean of the random variable expectation x given y is just the expectation of x. The proof is straightforward. Since expectation x given y is a function of y, its expectation is the sum over y in script y of the value it takes, which is expectation x given E sub y times the probability of taking that value, which is P sub y of y. This sum is sum over y of P sub y of y times expectation x given E sub y. We know P sub y of y times expectation x given E sub E is just expectation of x indicator E sub y. Summing this over all y in script y gives the expectation of x because the events E sub y partition omega. Now for continuous random variables, when x and y are continuous, we can define the conditional expectation of x given y as a continuous random variable. Expectation x given y mapping omega to r such that its value at omega is given by the integral over x in r of x times the conditional density f sub x given y equals y of omega of x dx. This conditional expectation, being a function of y of omega, will have a distribution related to the density f sub y of y. And the corresponding lemma law of total expectation for continuous y. For continuous random variables x and y, the mean of the random variable expectation x given y is the expectation of x. Let's look at the proof. Since expectation x given y is a function of the random variable y and y has density f sub y of y, the expectation of expectation x given y is the integral over y in r of the value expectation x given y equals y times the density f sub y of y di. Substituting the definition of expectation x given y equals y, this becomes the integral over EA of df sub y of y times the integral over x of x f sub x given y equals y of xd. From the definition of conditional density, f sub x given y equals y of x times f sub y of y equals the joint density f sub x y of xy. Substituting this in, we get the double integral over y and x of x times f sub xy of xy di dx. We can interchange the order of integration by Fubini's theorem, assuming appropriate integrability. Integrating f sub xy of xy with respect to y first gives the marginal density f sub x of x. So the expression becomes the integral over x in r of x times f sub x of x dx, which is by definition the expectation of x. Let's consolidate the definition of conditional expectation conditioned on an event space generated by y. Consider two random variables x, y on the same probability space omega script f p. First, the conditional distribution of x given a non-trivial event b generated by y, meaning b is in sigma of y is f sub x given b of x, defined as the probability of x less than or equal to x intersect b divided by the probability of b. We can define f sub x given b to be 0 for trivial events b in sigma of y that have probability 0. Second, the conditional expectation of x given any event b generated by y is expectation x given b equals the integral over x in r of x df sub x given b of x. Again, we can define expectation x given b to be 0 for trivial events b in sigma of y. Third, the conditional expectation x given y is a function of y, hence it is sigma of y measurable. It satisfies the crucial averaging property. For all events b in sigma of y, the expectation of expectation x given y times the indicator of b equals the expectation of x times the indicator of b. With this, we conclude the first lecture on conditional expectation. In the next lecture, we will look into the properties of conditional expectation.